Busoye from the Department of Statistics, University of Ibadan. He will be taking us on the topic Introductory Statistics for Biological Science Researchers in Nigeria and globally. But before I proceed, I would love to have a brief citation of our guest speaker. Our distinguished professor and his BSc Statistics, MSc Statistics, and PhD Statistics from University of Ibadan. He's also a certified statistician. He has taught in other universities, including Addis Ababa University in Ethiopia, Pan-African University in Kenya. His research interests include macroeconomic modeling, applied Bayesian analysis, and statistical model simulation. He is a consultant and research fellow to several organizations, both locally and abroad, including but not limited to the African Union, the African Economic Research Consortium, and the Lagos State governments. He is also a member of many professional and academic associations, including the Royal Statistical Society in London, African Econometric Society, and the International Biometric Society Group of Nigeria. His field of expertise include big data analytics, macroeconometric modeling for policy analysis and forecasting, risk and decision analysis, and Monte Carlo simulation. So before we bring in our speaker, I would like to call on the head of Department of Theriogenology to give a brief remarks before our distinguished speaker will continue. Thank you, sir.
Thank you, Dr. Dikoki. I want to welcome everyone online for you're welcome to this seminar series in the department, and I want to really appreciate our guest lecturer and the resource person. Thank you, Professor Olusoya from the Department of Statistics at University of Ibadan. He's a father, he's a scholar of many years, and he has been a mentor to many people. We are so privileged to have him with us this afternoon, and I really want to welcome you, sir. I want us to sit back and enjoy this seminar, and I believe that within the next 1 hour, we'll be acquiring new skills that will help us in facing some of the challenges we do have in our research, data analysis. And so I want to bring Professor Olusoya on board. Thank you, Prof. You have the floor, sir.
Thank you, sir. And good afternoon, ladies and gentlemen. For me, it's a great honor to be invited to give this talk. It's going to be just like a refresher course. Most of the things we are going to discuss are not new completely, but in a way, this is to retool and to possibly remind us of few things. So it's a pleasure to be on this session and to discuss introductory statistics for biological science researchers. So today, like I said, we will try to demystify few key statistical concepts and see if we can build your confidence in data handling and help you to understand how to select the right statistical tool for your research. But before I continue, let me just say that we have this laboratory established in the Department of Statistics, Laboratory for Interdisciplinary Statistical Analysis. I, with a few other colleagues, established this lab in 2015. So the idea is to support research, interdisciplinary research in the University of Ibadan. Most of us, we have our areas of specialty, but you struggle with statistics, techniques, statistical tools. So the lab, can support, and provide any assistance in the research value chain. So feel free to relate with us, and we will be glad to assist you. Even if you need a personalized arrangement, that can be worked out. So let's hit the ground running. And before we dive into today's, sorry, I'm struggling with my, just a minute, okay? No.
I think it's clear, sir. It's visible.
It's okay now, right?
Yes, sir.
So there are 4 fundamental questions, every biological researcher should ask and get correct answer. One is, what must I do after collecting my data? The second one is, what should I look for in my data? And of course, the third question is, which statistical or what statistical tools are most appropriate for my type of data? And then the last question is, which is very important, what are the common pitfalls and what are the good practices when it comes to data analysis? What should I avoid, and how should I go about some necessary or unavoidable obstacles? So these questions will guide our discussion today. So in practice, many researchers, once they get the data, they rush into statistical calculations without taking time to understand their data. We normally, those of us in statistics or data analytics, data is like patients, the way medical doctors, and of course you people are also doctors. So the way, if you are treating animal or treating human patients, the patients in statistics are the data before us. So what that means is that the data sometimes suffer from a lot of deficiencies. Just like human beings also do have health-related issues. So we see data as patients. And medical doctors, they have good habits, which we also borrow uh, in statistical practice. And that habit is one, to interrogate the patient, ask the patient questions, how the patient is feeling. Um, so we also interrogate the data. The whole idea is to understand the data very well. The second thing medical doctors like you also do is to examine the patient. You do that most often by checking some parameters. You can ask the patient to lie down. So you look at the temperature, so you press few things, and uh, so you examine key uh, organs. Similarly, we need to do that to our data. Examine the data properly. Not that the moment you have your data, then you rush into the surgical lab and start performing operation. No. The third thing that you have to do, of course, which medical doctors do, which we also borrow, is to conduct tests. So doctors will now prescribe certain tests, go and do this test A, test B, and so on. So the combination of three things will then help the doctor to diagnose the problem properly. We also do tests in statistical practice. So that those three steps, like you medical doctors, veterinary doctors, we learn a lot from your practice. We borrowed a lot from your practice. And that way, we are able to also understand our data very well. So bad practices include poor understanding of how measurements were taken. If you don't know how the data were generated, and all you just want is to rush into complex calculations and looking for significant, p-values, so that you can go and do Thanksgiving and all of that. So those are not bad practices. Um, they are not the best way. So good practices require understanding your measuring system, the instrument you use, the way the instrument works, and the error in the measurement. Knowing your data very intuitively, and then taking time to explore the data thoroughly before analysis. Before I continue, I have about 64 slides. I don't intend to I don't intend to cover all the slides. So I will stop when the moderator wants me to stop. And then if we have opportunity another time, then we'll continue. But these materials, they are in printed form. So those who want the printed copy can just take time to come to our lab. So that takes us to key diagnostic questions. The questions that you need to ask yourself when you have your data, when you have collected your data. So The first question is, how are my data distributed? What is the distribution like? This question is very important. Most of the techniques for conducting statistical inference, they are based on normality assumptions. Your T, your Z, most of these parametric tests, which we will talk about later, they are based on the assumptions that your data has a bell shape. So you need to ask this question: is my data normal? That is, does it have a bell shape, or is my data skewed? So the other question is, how much variability exists in my data? In other words, do I have wide confidence intervals or high standard deviation? I will need to explain this a little bit. When we talk about statistics, there wouldn't even have been need to study statistics or use statistics if we conduct experiments and the values are constant. In other words, they do not change. You conduct the experiment, the value is 20. You conduct again, please let's mute ourselves. Please let's mute ourselves so that we can enjoy this session. So if the values are constant and the values are not changing, then I will tell you that the next experiment, the value will be the same. And if in millennium years from now, that same experiment is conducted, the value. But what we do mostly in statistics is to understand the variability in our data. What makes height of human beings to vary? What makes the weight of animal to vary? So we are interested in the variability. And the variability can be one that is they concentrate around the center. No, the spread is not wide. They spread around the center. In that case, the standard deviation will be very small. But if they spread far apart from the center, then the standard deviation will be high. So we need to check our data in terms of what is the nature of the spread. How far away are the observations from the center? Whether they are wide or whether they are high. So the reason being that if the variability is high, then it is going to affect our precision. Variability is a function, precision is a function of variability. So we take time to really look at the nature of the spread of our data. You can also write your questions in the chat menu. Maybe the moderator can can speak to those questions later. The other question you want to really ask yourself is, do I have outliers in my data? It's just like you have data about age of students in the pre-nursery class. The question is, if in a pre-nursery class where you're supposed to have age 4, 5, 6, if you have age 10 in that pre-nursery class, or you have age 15 in that pre-nursery class. So two things could happen. The age 10 could be a legitimate age. That is, truly this person with this age belong to this class. Maybe he's starting late. It could also be a misnomer, something that is completely, maybe the figure got there by error, maybe while you are inputting the data or while you are collecting the data. So it's very important because outliers can influence the outcome. They can have very radical impact on the results. So you must check for extreme values in the data. If they come there by mistakes, you can do whatever is necessary, get rid and replace with the correct value, and then continue with your analysis. If they are there legitimately, you cannot remove because they belong there. So you might need to now look for other ways of handling that situation. So these three questions, they are very, very fundamental before, not after analysis. They are the few, they are critical before you even embark on the analysis. So that takes us to the issue of measurement skills. Measurement skills, why do we even have to talk about? Please, let's mute ourselves. Let's mute ourselves. Mute ourselves. Please, let's avoid interference at this time.
Yes, sir.
How do I know her name?
Okay. Yes, sir.
You can mute anybody. You are ready.
Men kò jẹ́ 40 kí women yìí so ẹgbẹ́ tó bá ti kékeré yẹn padà ẹ bó bá ṣe project yìí ló máa
Dr. Didi Olu, you can mute.
ti lọ fíìmù bẹ́ẹ̀ so àwọn nǹkan tá a máa lò yẹn ní kí bá mi ṣe.
Okay. Am I good to continue now? Am I good to continue? Wow. Is anybody?
Yes, sir. Yes. Yes, sir. Yes, sir. We are with you, sir.
Okay. Please just. The name is Oluwabusayo Rachel. If you can just get our attention to
The organizer can block him now.
Yeah.
They can mute him centrally. Mute the person
Dr.
centrally.
Didelu, Dr. Didelu, please mute that fellow.
So this oh my God. Okay. If you allow me, I will do what is necessary and let me see. Yeah, I think it's been she's been removed now. So no, she's not here. So I muted her. I hope she's not coming back. Sorry, I have to. So the issue of measurement scale, I'm sure most of us will know a lot about this, but often we wonder why we need to bother ourselves about knowing, the measurement scale, with our data. The reason why we need to really understand the measurement scale is because we need this scale to be able to determine what statistics to compute, what analysis we need to use or that is appropriate. So a valid scale must have identity, which means each value on the measurement has identity. This interference is terrible. This interference is, how do we address this interference?
Maybe the host should just mute everybody.
Yeah. Okay. So measurement skills are very important for us to.
Hello, Ganiyat, please, can you mute yourself, please? Ganiyat Oluwakemi, please mute yourself. Thank you. Prof, sorry, sir.
Yeah. So measurement skills are very, very important. We need to know them before we can choose the appropriate statistics to compute, or for us to know the kind of analysis that is valid for our study. So I said a valid scale must have four, any of these four properties: identity, magnitude, equal, intervals, or a true zero. These properties help to differentiate nominal, ordinal, interval, and ratio scales. So when we talk about identity, it's simply referring to each value on the measurement scale as a unique identity. Magnitude, which means it has an ordered relationship to one another. You can say this one is bigger, this one is smaller. So then equal interval is simply saying the scale unit along the scale are equal to one another. In other words, on that scale, the difference between 1 and 2 will also give you the same thing as the difference between 19 and 20. So we have equal interval on that scale. And finally, a minimum value of 0. So the scale has a true 0 point. Any value below 0 will not exist. So the least value on the scale is 0, and below it no value exists. So these four properties help to define the measurement scales. So nominal scale, for instance, the only thing it has among those four is that it satisfies the identity property of measurement. So when you take gender, for instance, it doesn't have values, so you cannot say one value is greater than the other. So it's only it's defined by identity. Religion, so again, it doesn't have in terms of ordered, or you can't say one religion is greater than the other. So we have many examples like that. So the only thing that nominal scale satisfies is the condition that the condition of identity. So that's how you know whether your measurement is nominal or not. You can have groups, but you cannot say one group is greater or one group is better than the other. For the ordinal scale, it will satisfy two properties. One, it will satisfy the properties of identity and magnitude. you will be able to say it has identity. For instance, you can say is first class, is second class. Yes. Magnitude, because you can say first class is better than second class, so to say. So there is an order in that measurement. So if those two properties are satisfied, the identity and magnitude, then it's an ordinal scale. And the popular one that we all know is the Lakers scale, the shoe size, and all of that. Then we also have the interval scale. The interval scale have equal, of course, it satisfies three properties: the identity, the magnitude, and of course, the intervals. So equal intervals, which means any 2 points on the difference between any 2 points on the scale will give you the same thing if you take any other points of different magnitude on the same scale. So the only problem, thing that is missing is that it does not have arbitrary 0 point. So no true 0. The 0 there rather is arbitrary. It has arbitrary 0 point, but no true 0. An example here is the Celsius and the example of temperature measured in Celsius and Fahrenheit. Ratios are meaningless here because you cannot say 20 degrees centigrade is twice as hot as 10 degrees centigrade. So the ratio ratio scale, which is the one that has all the 4 properties: identity, it has magnitude, order, it also it has true 0. So, and this is often the one we encounter in physical sciences, I think also in biological sciences. So, but I'm not too sure. I'm not deep in biological sciences. So, but in physical sciences, you have true 0. Velocity can be 0, acceleration can be 0. You can have true 0. Density, force, and not. So because the minimum value you can have in those examples is 0. They can never be negative. So you can't have negative weight and all of that. So those are the 4 measurement levels, and any biological researcher should be able to categorize and say my data is nominal, my data is ordinal, my data is interval, my data is ratio. And why this is actually why we are interested in this measurement skills, because there are some statistics that you cannot apply to those skills. So in this table, for instance, mode, if you are looking for mode, yes, you can. If the data is nominal scale, yes, you can talk about mode. In nominal scale, you can also get or obtain mode for ordinal scale, for interval. For ratio, provided uh, the result will be meaningful, but in most cases, you don't even talk about it here. For median, for nominal, you can't be saying you have the median. No, you can't compute median, so it won't make any sense at all. But in ordinal, yes, you can compute median. In interval, yes, you can compute median. In ratio, yes. When it comes to range, minimum, maximum, we don't use that when we are dealing with nominal data. But the rest, measurement can take that. The mean is also very selective. So you can't use it for nominal, you can't use it for ordinal. For interval, provided you are dealing with metric, measured data, but you can use it for ratio. The same thing if you are computing standard deviation. So it's very common for most early researcher, those young graduate students, computing the mean of gender, computing the mean of religion, so whatever. I don't know other things you compute, or maybe genotype, you are computing the mean and so on. So standard deviation, it won't make any sense. So that's why we need, from the onset, to have a good understanding of our data. Look at the measurement scale. So just as you need to know the measurement scale, to be able to determine the statistics to compute, you also need the measurement case in case you want to do data visualization. You want to visualize your data. So there are graphs, charts that are most suitable for different measurement scales. For instance, in this table, if you have data that is in ratio, it is wrong for you to be using bar or pie chart. No, for instance, if you are talking of age and you are using bar chart, at best you can only categorize the age, create age group. Maybe income, you can create age group. You can income group and so on. But in the raw form that you have it, you can't apply ratio because you will have too many bars. The same thing if you have pie, you will have too many pie, and then your visual becomes so routed, so confusing. You won't be able to really make sense of that. Now, visualization like stem and leaf display, you can't use it for nominal data. And they are very good. They tell you a lot about the shape of your data. They can also help you to detect outliers so easily. They can help you to draw preliminary insights from your data, even without doing any rigorous calculations. So box plot, histogram, all of this, box plot, you can't use it for nominal, but you can use it for ordinal, interval ratio. Histogram, no go for nominal, no go for ordinal. Well, for interval, if it's in metric, in other words, if it's measured, and then for ratio, yes, you can use it for ratio. So it's applicable to that. So these slides, this particular one summarizes the recommended statistics and graphs for each scale using examples. The key idea here is that always match your statistical method to the type and properties of your data. Know the properties of your data and match the statistical method you are using to the type of data that you have. This is just the continuation of that table. So we see more example. If you have interval, these are the properties, and of course, these are the examples. Thoughts, behavior, feeling. This may not be directly related to biological, but you can also think of examples. So if you have interval, you can do frequency. You can get mode, you can get median, mean, standard deviation, and so on. In the area of graph, you can use bar, pie, stem, and leaf, and so on. The same thing, this is for ratio, and these are the things that you can do. So, earlier I mentioned the fact that most of the statistical method we developed or used for drawing inference, for testing hypotheses, they are based on key assumptions. They are based on key assumptions. So these assumptions, they have to be checked. They have to be tested before they can be used. If you don't test and confirm, establish that the underlying assumption is established, that the underlying assumption is satisfied. If you go ahead and use the test, that will render your inference invalid and spurious. So every statistical test is built on assumptions, and violating these assumptions invalidates your results. So always ask this question before you use any statistical test. Before you carry out any statistical test, ask what are the assumptions that must be met. 2, have I checked the assumption whether my data satisfy the assumptions? I need to ask that question. So even when our colleagues are working and so on, and is presenting, those are questions we can use to establish whether due process is followed, whether best practices are followed. The third question is, if the assumptions are not satisfied, that's not the end of the road. I mean, it's not to say that you can't do research any longer, but you need to now ask yourself, what then is the remedy? What is the way forward? It is not the end of the road, but we need to be sure that one road is closed before we open another road. So this is foundational for credible research. This is very important for credible research. So that leads us to 2 broad classes of tests. And I know many researchers struggle a lot. So these 2 broad, all tests, all statistical tests, if I would say in heaven and on earth, but I don't know, but let's just even say in heaven and on earth. All statistical tests fall into two broad classes: parametric tests and non-parametric tests. What makes parametric is that the development of that test assume normal distribution and other very stringent conditions. So parametric simply means that there is a distributional assumption. Non-parametric simply means there is no distributional assumption. So parametric, assumes we assume a normal distribution. And is it only normal distribution that we have? There are countless distributions. But normal distribution possesses some fine properties, very fine properties. That's why those who develop most of these tests prefer to work under the assumption of normal distribution. Other distributions, they are skewed one way or the other. Yes, So therefore, they are not. They are difficult to. So for non-parametric, the assumptions, not that it's completely free of assumption, but no distributional assumptions. So no, it's not mandatory, it's not compulsory that the distribution must be normal. But there are other assumptions, very few in number. So the other thing about the two is that the parametric tests, they are more powerful. So you can't run away from them or bypass them and then go to non-parametric tests. You will still do few things before you go, even if the underlying data is not normal. It may be because you have fewer data points. Maybe you need to collect more data, and that most people are not willing to bear the extra cost of collecting more data. So they want to do, it's like if you already use your lab, you have just 10 rabbits or 20 rabbits, and then you collect the data and it's not normal, then what it requires is that maybe you need to take more data points and so on. So often the cost of getting additional data point can be the reason why people get discouraged. But for this discussion, knowing which applies is what is central. Is so when you are choosing the correct method. But if you are looking for test that is powerful, give you better result, then parametric test. So all you need to do is to satisfy the conditions. But if you can't meet, then you know that you are opting for less powerful test when you go for non-parametric. So it's a trade-off that you must be willing to take. So most of the issues here I've talked about them. So, But when we talk of parametric tests, as I said earlier, tests like the t-test, which we use often, the ANOVA, all these tests, they require normality assumption. Your data must have a normal shape, and they are most powerful when those assumptions are satisfied. But when you have small sample sizes, then you are likely going to have normality assumption violated. So the more sample you have, the more likely you are going to satisfy this normality assumption. So small sample is good. Do we start taking questions now? I can see. Okay, let me allow you to make it a bit interactive. Yes. Somebody is raising up hand. Or is it in error? Akamu, Olorunsho, your hand is up. Is it in error, or you have quick interjection? I think it's in error, but if there is any quick interjection, that can be taken. So the point is that if you have very small sample, you are likely not going to be able to satisfy this normality assumption. So it's good you have data point, if possible, greater than 30. So because if it's less than 30, you are likely not going to. So empirical evidence has shown that with observations greater than 30, you are likely to satisfy the normality assumption. So anybody using t-test, anybody using ANOVA, whether one way, two way, whatever number of ways ANOVA, it is very, very important to check the underlying assumptions. But if you have checked the underlying assumptions and they fail, and you cannot collect additional observations, then you can opt for a less powerful test, the non-parametric test. So we use it when the parametric assumptions fail or cannot be satisfied. But they are less powerful, so it is not a safe haven, so to say. The other problem with the non-parametric test is the interpretation can be more difficult compared to the parametric test. So because many of the tests use rankings of the values in the data and not the actual data. So which means, unlike the parametric tests that are based on the actual raw data, the non-parametric will still need to transform and use the ranking. So what are the parametric tests? You have the Wilkinson rank test, Mann-Whitney, Kruskal-Wallis, and chi-square test, Friedman test, and all of that. So they are not the first thing to consider. They come as a fallout, not what you should go for in the first instance. So let's now look at those assumptions. I told you parametric there simply means normality or distributional assumptions. But there are other assumptions. One, the assumption of equal variances. That's what we call homogeneity of variances. So most of the times when you are performing your biological experiment, you have groups, maybe treatment groups. You also have the control group and all of that. So you can have different groups, but if you are comparing the groups, the underlying assumption is that the group variances are equal, that the group variances are equal. So this assumption is very important. We'll see. It's common to see a lot of studies and so on not taking the pain to check these fundamental assumptions. The other assumptions that most people take for granted, and they are very, very important, is that the observations are independent. That is, the observation 1 is not influenced or does not influence observation 2. So if I'm collecting, let me say, I might be wrong, observing weight of rabbits, for instance. So maybe I'm feeding them with different diets. So this assumption is saying that the weight I observe on the rabbit 1 will not in any way depend on the weight I observe in rabbit 2, which means the weights occur independently. The weight occur independently. So one weight does not influence another weight. I think that example should be clear enough. But most often, we skip these preliminaries when we are dealing with our data. You see people immediately, they collect the data, they run t-test, they run ANOVA. Those things, anybody, analyst on the street can do them for you. Even yourself these days, you put your data in ChatGPT to analyze, but doesn't make it scientific. So apart from normality assumption, which is critical for parametric test, when you are testing differences between two groups, homogeneity of variances, assumption is very critical, which is saying that the spread around the mean, around the center for group A, maybe for treatment group, is the same as the spread around the center for the control group. That is when you can compare whether group is group A is different from group B. So, and then the assumption of independence. So these three assumptions together, they are key assumptions of parametric test. That takes us, I will soon, wow, this is 2 o'clock already, but I don't know. We might soon stop. Just let me finish with this part. This is part 1. So this table is just helping us to select a non-parametric that is equivalent when parametric assumptions fail. So you have, for parametric test, you have, if you are testing one sample, then you can use Z-test, you can use T-test, but the assumptions, the 3 assumptions must be satisfied. The underlying distribution must be normal. Of course, since it's a one sample, the variance, for Z to be used, the population standard deviation must be known. It's only when the population standard deviation is unknown, that's when you use the T-test. But if the assumption, and then you expect, the third assumption is that the observations are independent. So independence simply means randomness. So because we will still talk about that later. When we say observation is independent, it's simply saying that the observations occur randomly without one influencing the other. But if the assumptions fail, then these are the corresponding non-parametric, so the equivalent non-parametric test that you can use. To save time, let me just move on. The same if you are dealing with one-way ANOVA, these are the Kruskal-Wallis test and Moore's median test. They are non-parametric equivalent for one-way test. If you are doing two-way ANOVA, then the Friedman test is the non-parametric equivalent. And I'm again reiterating the fact that this is where to start from, the parametric test. Not that you start from the non-parametric. It is when the road is closed here that you open this non-parametric, if you are genuinely interested in having test that is powerful. So the assumptions, the test assumptions. So how do we know whether the assumptions are satisfied or not? So that's what this slide is trying to test. So we need to, before we can say we are going for non-parametric, we need to check the assumptions. Assumptions of normality, assumptions of homogeneity, equal variances, assumption of independence or randomness. So we need to check them. And these are the tests that you can use to check for normality. You can do the skewness and kurtosis. You can use the Shapiro-Wilks test. You can use Kolmogrove's. In fact, for anormality, the truth is that we have over 100 tests that can be used for checking normality. Over 100. They are just there. Many. So, but a few of them, are popular, as those are the ones listed here. If you have to check whether for homogeneity, whether variances, group variances are the same, then you use the Leibniz test. So it helps to check whether the variance between the dependent variable and the independent variable is the same. So for randomness, we use the run test to check. So let's say the normality assumption fails, then of course you can do few things. Check if you can collect more data and see whether that will change. Sometimes also we do transformation, but we can't discuss that at length here. So, but if the homogeneity fails, again, there are a couple of things you might need to do. So, you might have to take more data also. There are also some tests that can handle that when you have heterogeneity, so that can be corrected. So again, randomness is very important. You just have to satisfy this one, randomness. So most of you must have had IID, independently and identically distributed. It's just talking about the fact that your data is random and the data has the same distribution, which is in most cases normal distribution. So if assumptions are not met, so these are the options that you can go for. So one, you can look at outliers, check for outliers, and either you remove or you justify the existence of outlier in that situation. You can transform the data. I mentioned that earlier. You can also run the test despite the failure of the assumption. There are some tests that are robust to the violation of the assumption. So even, for instance, the t-test, even when the data is not normally distributed, t-test and ANOVA can still be used under many circumstances, under some circumstances. So you can use alternative, that's non-parametric. You can switch to non-parametric methods. So, but in that case, your choice will depend on the severity of the violation that you are dealing with. So before I close, let me just attend to two, three more slides so that I can take your questions. Of course, that will just take us to about 1/3 of what we have here. Most of us must have heard about exploratory data analysis, EDA. It's always the first step in any statistical workflow. It helps to identify outliers, errors, and to know the distribution patterns. So you can detect coding error, missing values, entering, inputting errors, odd values, and so when you conduct exploratory data analysis. This is where you will even know where a researcher is truly in charge of his or her data. Just today, we just had a conversion exam, at CP, and I was saying that in research, virtually everything apart from the data, you borrow every other thing. You are going to borrow the literature you will know. You are going to borrow the method you will use. You are going to borrow all the things. Most often, particularly in biological, the only thing that will possibly be your own thing, that is just your own, is your data. Most of the times, it's your data. Because it's your data that is helping you to generate new evidence that you want the scientific community to accept, that yes, my data is giving us new insight that other researchers have never talked about or discovered. Every other thing, the method, the process, and everything you follow, the protocol, wherever you follow, they are borrowed. But the data that you gather is one that you own, as your own. And therefore, that data integrity is very important. That's why for some time, our lab, we've been doing radio program called Data Speaks on Diamond FM. So tomorrow we have another edition between 2 and 3 p.m. So EDA helps you to get more insight about your data. And then it helps to identify what is really happening. So you risk drawing conclusions from flawed data if you fail to do the exploratory data analysis. Then the question is, how do you do the EDA? By just generating plots like histogram, box plots. These are preliminaries. Even when I review for most journals, researchers keep all these things. They go to the very complex models, complex techniques, and then the technique will now disappoint them. They will just discover they have nuclear weapons, but they are unable to kill the rabbit that is disturbing them at all, because they can't use the so that has always been the greatest challenge. So histograms, box plots, stem and leaf plots, frequency table, all these simple things, they help to understand our data. So you have the first clues about data quality and structure. Very important. So you generate basic statistics like minimum, maximum, mean. You will see that some data you are not expected to see. Minimum zero should not be there. Then you suddenly see zero there. It should not be negative. You see negative there. So EDA can help a lot. And then finally, how do you check for errors? Always check your data for errors. Confirm the ranges. If you are looking at weight, what do you expect to be the minimum wage? The minimum weight. What could be the maximum weight of a rabbit? What could be the minimum weight of a newborn? What could be the maximum weight of a newborn? No, simple checks like that. Confirm, verify the means. No, inspect missing values and carefully check for outliers. Many research problems stem not from analysis but from data entry mistakes. I think I should stop here. I still have part 2. I have part 3, but this is where we might call it a day. Thank you very much.
Thank you so much, Prof. We really appreciate the seminar, sir. It was very deep, sir. We appreciate you, sir. So we would like interested people to ask questions on what we've learned so far. So if you have any questions for Prof, you can just signify so that I can relate it to Prof. But I hope Prof can also see the comment section, sir.
Except
Prof,
I stop sharing. If I can.
Okay, Prof, don't worry. No, don't stop, sir. I would read it out for you, sir.
Okay.
Yes, sir. Do we have questions for Prof? Okay, I can see Akomu for Longshore, but I can't see your. You can unmute yourself and ask Prof your questions. Akomu for Longshore, any questions? You signified your hand. I'm not sure is with us yet. Okay. Do we have any other questions? Prof, sir, please, we will still like to have the part 2 and part 3, sir. Hello, Prof, sir. Can you hear me, sir?
Yes, I can hear you. Only that
at a convenient time, sir.
Yeah, that's possible in future.
Okay, sir. Thank you so much, sir. I don't think I have questions here. I've been checking.
Maybe people did not understand. It's either
no, not really, sir. For me, it was very interesting. But okay, maybe I should break the ice by asking my own question, sir.
Okay.
Yes, Prof, for we in biological sciences, I understood the parametric and non-parametric test. But the question I have is, under what circumstance, though you said we should always start with the parametric test. Yeah, but under what circumstance would we go for the non-parametric?
Yeah, so I think I mentioned it.
Yes, you said if we have data greater than 30.
Yeah.
Yeah,
so,
but is that the only criteria, sir?
So, and I said if there are not just one assumption, so the starting point is for you to look at the parametric test. So, and you have to conduct the normality test, check, conduct the homogeneity of variances test, check, conduct the independence of randomness test. And based on this test here, and I said here, that if assumptions are not met, that's not the end of the road. So you can now first check for outliers, because that can also be the cause of the failure in the test. 2, you can transform the data, even transformation like taking the log to make the data that was originally not normal to become normal. There are other types of transformation. Then there are still some parametric tests, and I mentioned here that even t-test and ANOVA, they can still be used. Even though they are parametric, they are still robust. So there are some tests that they are robust despite the fact that the assumptions are not satisfied. They are still robust. So you need to check, you know, and then when everything now fails, then you move to the alternative test, the non-parametric. So that's the steps I recommended. Doc.
Okay, sir. Thank you, Prof, sir. Yes, sir. Then someone asked for permission to get the slides. I know you mentioned that earlier, sir. But
yes, I can get you this part that we have covered. May be able to send to you. But I said also that we have printed copies in the lab if you are interested. But if you also want this stuff, you can. I can extract this part 1 and send to you.
okay, sir. All right, sir. Thanks so much, Prof, sir. I would like to call on the head of department for his closing remarks, since we don't have more questions for now. So if there are any other questions, Prof, I will send it directly to you, sir.
No problem.
Thank you so much, sir. It was great having you, sir.
Thank you for.
Yes, sir. Thank you, sir. Head of department, sir. Hello, sir. I'm not sure he's Dr. Janisa. Hello, sir. Okay, he's not responding. Maybe he's engaged with something. So on behalf of the Department of Theriogenology, hello, sir. Hello. Okay. On behalf of Department of Theriogenology, I would like to appreciate everyone that participated in this seminar series, most especially our invited guest, Professor Olusoya Olubusoye from the Department of Statistics. Thank you so much, sir, for coming. We learned a lot, especially some of those new terminologies. We hope we'll have another opportunity to learn from you, sir. I would like to appreciate everyone from the department, Professor Iyeni, and other staff. I saw Dr. Moyi and some other staff of the department. We want to appreciate you for joining us. And to our guests from outside the department, we are so glad to have you. And we hope you will join us when next we'll be having our seminar series. Thank you so much, Prof. We are grateful, sir.
Thank you very much.
Yes, sir. Thank you, sir.